Yeah, well, thanks, Rich, for the intro, and thanks for having me, and everybody, welcome, and thanks for listening to this. It's a big pleasure of mine to show off a little bit of what we've been up to recently in big data, SAR data processing, and certainly getting exposed to the Pangeo ecosystem has been a big boost for me to see how I can actually visualize these tremendous new data sets. I titled the talk, The New Era of SAR Time Series. It's really amazing how we have matured and are finally in the stage of an operational observing system of our planet. SAR has been used for mapping the universe since its early stages. Radar missions have been used to map planets all the time, and it's been difficult to get that going on planet Earth. As a former program manager at NASA once said, getting the resources for Earth system science would be much easier if Earth was a different planet. But so anyway, I think we finally reached a stage here where we having an enormous amount of SAR data. I've been involved in that for many years, since my early PhD years, actually the diploma years in Germany. If you wanted to know more and find out about my background, they actually did a nice feature this month up at the Alaska Satellite Facility DAC. So if you go to the NASA DAC at ASF Alaska EDU, down at the bottom, they're doing a feature on my involvement with that NASA DAC and SAR time series. But I won't get much into detail.
Spencer, hold on a second, Joseph. Spencer, can you, I don't have the ability to mute for some reason. Can you mute everybody except Joseph?
Okay, give me a second and I will.
Okay.
Okay, I unmuted myself. Can you hear me again?
Yeah. Yep, sounds good.
All right, good. Yeah, so there's that. But briefly, just what makes SAR so exciting? What I am so excited about is really a couple of things. A, it's an all-weather mapping tool of the planet. So the microwaves do penetrate the atmospheric clouds, which also means all-season monitoring. Think about ice dynamics in Arctic and Antarctic winters that we can monitor. But certainly it's a fully coherent active remote sensing technology, which means we measure phase and magnitude of a signal. And with the coherency, we can do applications like interferometry, in addition to the backscatter metrics, which I mostly will focus on in this talk. We've done a lot of analysis on these time series of magnitude analysis. But most recently, and we can maybe after the discussion talk a little bit more, I've also been involved in more of coherent measurements and metrics. So we can accurately calibrate SAR over space and time, which makes it a really interesting tool to study these time series signals or time series signatures of various targets on the planet. And that consistency of measurements is really what allows us to study those signal changes, and really they relate typically just to changes on the target if we keep the illumination geometry of the SAR satellite the same. So a SAR satellite that measures in December, or that measures at 6 a.m. or in June or in the afternoon, if this orbit is the same, if the viewing geometry is the same, what we measure on the ground is the change of the target. And that's the interesting thing here. And if we think about it very simplified, these changes in the signal are really a change in structure or moisture. It's the dielectric that changes. And those we can relate very complementary to optical system. And so once we have a tool that measures moisture and structure changes, that of course opens up a range of interesting applications to make it an invaluable tool for monitoring our planet. So the applications in science, but natural resource management, but also reaching now into policy decisions at local and global scale, I think are quite fascinating. I've been involved in the early briefings of the UN climate body in Bali in 2007. I gave a talk on how we can use radar data for the reduction of emissions from deforestation, forest degradation, because of course one of the key issues is tropical forest monitoring, and here it's cloud covered, right? So SAR is an important tool that features in that aspect as well. Just a quick example of that cloud penetration capability. That was a lucky shot of Sentinel-1, the European sensor, in 2018, when on September 14th, Hurricane Florence made landfall. And you see actually the eye right at the landfall. In the larger satellite swaths, you actually see already the not only the wind pattern on the water, but also already the moisture changes of the heavy rainfall of the 100+ kilometer cyclone that hits here land. But also if you zoom in, you see the flooding already happening in the streets of Wilmington. And if we then enhance the signal on the background and the noise itself, you see sort of the circular wave pattern, and study those under the hurricane here. So something you wouldn't, of course, see with any other optical satellite because of heavy cloud cover. A quick example also now from a static image to what the dynamics are. This is an example over the tropics, monitoring a tributary to the Amazon. This is the city of Yurimaguas. I'm animating here an acquisition every 12 days in two polarizations. And in the fall of 2017, early 18, you see a breakthrough of the river happening here, and a what I call the burst of an oxbow lake. The meander broke through and it starts to erode at the other side. And so we actually can monitor really those changes quite dramatically with the sensor. So you see here, that's a newer optical image that was acquired around the cloud-free days, where you see that where the breakthrough had happened. But with the time series, we were actually able to see exactly when that happened and what sort of the speed of that erosion was. So that makes the time series so exciting. What's key, however, and what we need to acknowledge is precise processing of the data. And from the get-go, I set out to do that. During my PhD, I developed my own ortho rectification software. But now we have some really high-end software to help us and also bring cloud processing together, so we can develop fully automated processing chains to build these highly accurate time series. And there's main criteria are we need excellent geometric accuracy to overlay the data if we want to really look at time series signals or fuse it with other sensors, etc. So it's what I call the real estate principle: location, location, location. So we need to be absolutely accurate in that context, but also do an excellent job on radiometric calibration if you want to look at that stability over time, which means take care of the noise floor, takes care of scattering area-based pixel calibration, take care of incidence angle, etc. Whatever is sort of pertinent to radar and SAR imaging, we need to make sure when we want to have highly accurate time series to have that done. And we've developed these fully automated and cloud-capable processing chains to allow us to do that. And then once we have a time series that is highly accurately calibrated and the pixels fit together, we can also then apply post-processing filtering like multi-temporal speckle noise reduction that allows us to preserve spatial and temporal detail quite nicely and reduce that infamous speckle noise in SAR imagery. So here's an example of ALOS data. So with all that, we can scale up and we can processing through cloud resources the entire planet. So here's an example of a map we did on all of 2017 acquisitions. I think it was 250,000 Sentinel-1 scenes that we processed. This is sort of the median backscatter of the entire year. In red, the like polarized data, which means same transmission and same reception of the antenna. In green, we measure in one polarization and measure the 90-degree return magnitude, so which we call cross polarization. And then we can do a blue ratio of those two because that's the two measurements we get, and you get these typical impressions where you see very nicely dynamics on the planet, except, for example, relationships to high biomass, low biomass, certainly desert areas, and so on. And that allows us then to go, if we have measurements every 12 days, which Sentinel-1, for example, delivers, we can look at the temporal signals. And here it's just an example of Burkina Faso, one of the subsets. We process everything in tiles, either geographic or UTM tiling scheme based in the Military Grid Reference System, MGRS, which is UTM based. But here's a tile, and once we have those, we can go in and pick any point on the ground and look at what the temporal signature is like. And we see what urbans look like with high backscatter, dense forest. And as the forest opens up, we see more through the seasonality of moisture changes in this more arid environment. But also, yeah, we can do that, of course, at many, many locations. And I'll show in the notebook example briefly then with the Pangeo tools, how we can point and click in these visualization more actively. Just recently, I got involved with NOAA and helped them on flood mapping. And so we studied, of course, hurricane impact at the Gulf Coast. Here's a quick series of 4 cloud-free optical images at very high resolution. Look at the coastline here as I flip through these. And then at the end, I want to show you a SAR time series signal over exactly the beach. But you see that since 2016, the coastline had actually eroded quite a bit. So you see, I flip back and forth a little bit, you see sort of clearly the erosion of the coastline here. And when I look at the Sentinel-1 signal of that beach spot here, and I did a false color composite where you see sort of blue what was the latest acquisition. You see sort of the change in that signal, but we clearly see that erosion trend in the SAR signal over time. So every 12 days, a measurement. Of course, we have tidal effect. Sometimes we have wind that changes the roughness of the water, hence the structure, hence the backscatter. But the trend is clear. It's very typical that we have that kind of flexibility to measure those kinds of things. And we have all sorts of applications. So our challenges are with the SAR data availability exploding, thanks to open data policies, we need to come up with cloud-based strategies on how to convert these data streams to analysis-ready data. And we need visualization and analytic tools to reduce these high spatiotemporal resolution data streams into meaningful presentations of the data and analytic tools of the data, both online and offline. And yeah, the data are exploding with the NISAR mission that we're going to launch, an L-band radar. We're probably launching end of 22, early 2023. Probably looking at 100 terabytes per day of science data volume. This Sentinel data, for example, right now we're looking about at 1.5 petabyte per year or 4 terabytes per day to analyze globally. So we want to harness these excellent suites of open source tools that are, for example, developed by the Pangeo group here and Q Hub from Quantside and friends that have been so helpful in this. So with that, I'm going to switch over here to my notebook that we've put together. Rich was involved here with me to look at an example here of looking at illegal gold mining in the Madre de Dios region in Peru. So we have processed a suite of individual tiles. I have a tool here that lets me, based in Bokeh, that's a website, and GeoPandas, etc. So here I have a suite of tiles processed all over the planet to look at different ecosystems, and we're going to look at one of these tiles in Peru to see what's going on in the landscape there. So let me switch to that. It's a notebook that runs on the latest version of the Q Hub, Jupyter Hub that we have set up here for eSIP, and it's latest version 0.3 and runs like a charm now. And we're pulling in all of the good tools here to analyze some of the data. At first, Rich put a little block in to show, so we're loading and we're creating clusters, and we're connecting to the cluster, and we scale the cluster. I think it's already it's running, so I don't need to even do that. And here's my clusters. I have 10 workers running. So here's a little block that shows uses stack for satellite search of the Sentinel-2 data, not the optical data. And if we look for the time frame, the same one that I had available for the SAR data here is 445 observations over that region. But when we filter that for a cloud cover percentage of less than 5%, we're left with 37. So it's a pretty cloudy region. I mean, obviously, always complementary to look also with optical data. But in this study region, SAR is certainly a good use case. My data streams are, when they go through the processing chain at the end, they get now converted to a SAR format. Hey,
Joseph?
Yeah.
Could I just suggest maybe that you clear the output, because it's just a little confusing to see the output before you execute the cell, you know what I mean?
Oh, I know exactly what you mean.
Okay. Yeah.
Serial output.
Yeah. Awesome.
So, yeah, so, and you just want me to do this live, right? Which means, I mean, I have to run through here, right? The cluster's still there, so that's good. Yeah, so here we go. So this is all live. And here we're connecting to a S3 file system where I have here's an example of one of these SAR tiles. And so we're looking at different SAR files that are available in this or SAR stacks. Here I have basically 4 different radar time series stacks, 2 polarizations, which is indicated by the cross-polarized or like-polarized indicator VVVH, and then a ascending or descending flight direction of the satellite covering that area. Empty fill means it has been multi-temporally filtered. The data are stored natively on the cloud in the format as scaled amplitudes, which means, and here's some formulas, and nice, of course, with notebooks, we can put in our LaTeX formulation. So we have the formulas to know how we convert from our digital numbers to our power units that we need to analyze, the physical units that we need to analyze the data with. So what I do is I just basically take this formula and loop over all these SAR files to basically say, whenever we read those in, we want to convert those to real physical measurement units. And with the delayed processing, of course, I just issue the command and then say this would be applied to any of these SAR data sets.
Hey, Joseph, sorry to interrupt again, but I think you might need to update the endpoint for your Dask cluster in the dashboard.
I'm not sure.
Because, maybe you're not doing anything with Dask yet? I
don't do anything yet. I just was reading it.
Okay.
But it might still be the case. We'll see. But yeah, so anyway, we're picking one of these data sets here, and in this case, I'm just picking the descending mode, like polarized data, and I get description. I have 115 time steps times 5490 times 5490 pixels in this data set. We can do something like how big is it? 13.8 gigabytes. And then I can go through and say, what do I, that was an experiment that I don't need. I set some cartographic reference system, and here I make a plot, a call to hrefplot to basically show me that time series stack on a background of tiles, optical Esri imagery. So let's see. So now I'm doing something and the workers start to be active, but I ran into that earlier, that I do need the task stream to bring in again. That's easy. Let's see here, tasks to see. That happens once in a while that you need to do that. Okay. Is that good enough, or you want the progress as well? Task stream's good, right?
That's good.
Yeah. just to ensure it's live, right? So here we are. This is an image of this heavily illegal gold mining region in the Madre de Dios region in Peru. And what you see here in these black streaks, those are really clear cuts of tropical forests where on riverines that get completely converted to bare surfaces with pools of water that are then used for gold washing. So unfortunately, all the river systems are highly toxic now from the mercury impact. And of course, the progress of the deforestation is something that we also are keenly aware of and want to help mitigate and stop. So here's my time series slider. So this is the image in what it looks like in November 2017. And I can go to the beginning of the time series and pick out my 2017 January image, and it should kick into gear and read that. And so here we go, and you see now that I can zoom in with these excellent tools, I can actually zoom into this region and get the full resolution eventually. So you see here's basically these braided river systems that you see come in here that have not been deforested, but where the yes, Rich, I'm turning off the hover tool.
Thank you.
And we're seeing here the before it really got logged, and then as I said, if we then want to go to the end of the time series here, we see how this entire area, for example, has changed. So I can of course go and build some subsets here and look at, for example, two images, the first and the last one in parallel, which is often very useful in analyzing these data sets. So here I'm just basically preparing myself to take the time step last and first. And once I have these two images prepared, I can put them next to each other, first plus last, and here they are. And what's nice, of course, is if I zoom into one of them, yes, hover tool off, we're picking both, right? So that's, and if I move around, we're doing that in parallel. So a very nice technique, thanks to the tools here, to allow us to compare two images side by side and flip through them. What I'm, of course, also interested in is now clicking into any of these images and look at these time series. So that's my last example here. I prepare an image that I tie together with the streams, all of you streams, and tap objects, and build that stream that I then want to connect. So here's an image, and here I define my time series function at any XY location that converts inside the images to the correct decibel scale. And I use the method nearest, so wherever I are, I pick out the nearest point in the time series, and that allows me to then connect the stream, and that is what I can visualize. I build a visualization with the panel column function here, and then use the servable visualization tool, and I'm building a servable that has a subset of the time series, and now with a fully connected to an extraction of my time series of the two ascending and descending and two polarization curves. So if I now zoom in again to let's say this particular region here that I know has undergone tremendous change, and I click in any of these points, it tells me at that point where the cursor is, when has that degradation actually started to happen, and I know immediately this is the conversion started in April, around April 2017. So this is, and if I click outside of it, I see the undisturbed signal on what I would expect if things hadn't disturbed, and so I can of course go through at any point and detect the early and the further we get away, of course, the later that disturbance happened. So yeah, with that, I can go anywhere, and what comes associated with the gold mining is of course also more settlements and all sorts of disturbances that start to happen anywhere. So this was a settlement or a degradation that happened fairly late in July 2020. So I'm using those kinds of techniques, the notebooks, these tools all over the place. It's a very simple, of course, to swap out these tile IDs with a different tile ID to look at coastal erosion, to look at flooding, to look at agricultural developments, etc. And it's been really quite powerful. So maybe quickly back to the PowerPoint here. If you want to study up a little further on radar, in particular with an aspect of forest related resources, but the first chapter has, or the second chapter has an general introduction on spaceborne techniques. We've put together a handbook funded by NASA Servier with several chapters. I wrote chapter 3 on SAR data for mapping forest and forest degradation. And if you want to contact us, I have a colleague who works with me in Latin America. Here's our contact info. And that's all I have.
Excellent. Thank you, Joseph. We can
You're welcome.
stop the